Hey everyone, so I'm joined by Tom Petersen from Intel. We've done a lot of these now.
We have.
And we're going to give you the preview of what we're getting into. So this is super cool. This was my favorite slide from your presentation.
Thank you very much. Damian did it.
Damian did this excellent job from Damian. Yep. So the reason I like this slide is this is looking at a single frame from Fortnite. Is that correct?
Yep.
And the part that was cool about it was kind of highlighting this difference between two devices where you can start to attribute what function is actually providing the uplift.
You're absolutely right.
And so that's the main thing I want to ask questions about, and then you all will get to learn about it as well. Before that, this video is brought to you by Squarespace, and visiting squarespace.com/gamersnexus will give you 10% off your first purchase with them. We've built a number of our own websites with Squarespace, where we list catastrophic PC hardware failures to inform subscribers of those failures. We also built our store website with Squarespace using its built-in e-commerce tools, and of course, we built a website for our CEO, Snowflake, because she demanded our audience know who really runs the show. Get to the core of your idea and spend less time on web design by signing up at squarespace.com/gamersnexus or click the link below.
This is where we were, our Xe core. Many people know it as Arc Alchemist. And we used our Xe core. It was the first time we scaled up our engine. It was a lot of work just to go from integrated graphics up to a big. So we had a lot of work to do. And we redid our software stack, but we didn't quite get everything done that we want. As you know, you gave us a lot of feedback. It was painful. I learned a lot. Now, we have all been focused on efficiency. So now the silicon that we built on Alchemist has been redone, and we're now using Xe2, and we deliver higher utilization, better work distribution, less software overhead. Whole new software stack is pretty exciting. So.
Cool. Yeah, and I think we reported on Xe2 around Computex with, maybe it was Lunar Lake?
Yeah, Lunar Lake, okay. Exactly. There's a whole architecture deep dive we did.
Yeah.
Really good. So after that, you look at a block like this, and I use this to describe to a lot of people what did we do, and you can see we changed pretty much everything. We've increased sizes, with better performance. So we did a lot of microarchitectural analysis on that, but people have said, that doesn't mean anything to me. All these words, gobbledygook, larger cache, SIMD, whatever, so what does that really mean?
Yeah.
So that's what this slide's all about.
Okay. Let's go back to the other slide.
Okay.
So, first, the quick kind of overview on a block diagram for this. So, has anything significant changed from the Alchemist block diagram in terms of sort of the structuring or the organization?
No, the organization is very similar. Okay. Our tile is basically called a render slice. And if you're going to build an SoC, you basically start with how many tiles do I want? And normally when you're doing cut down versions, you cut full tiles. So that's our top level. Within a tile, our computational element is an Xe core. That's where all the math happens pretty much. And there's usually some other logic associated with an Xe core. In this case, a ray tracing unit and a thread sorting unit and a sampler are all kind of fixed to one sort of Xe core.
Right.
And then we'll have 4 Xe cores per render slice.
Okay, cool. And then XMX, we actually talked about last time. I think we did some media discussions.
Oh yeah, XMX is a huge part of this. It's actually designed for AI acceleration. It's a systolic array, and we use it for our new features like XeSS2, which is super cool for AimJet. But really, it's another way to do math. We do vector, matrix, and regular sort of fixed function exponentials.
At risk of sounding like I have no idea what I'm talking about, what is a systolic array? I know the word systolic. Well, I only know it from blood pressure.
It's exactly the same though.
Okay.
That's where it comes from. So
I don't know what it means there either.
It's somehow pumping. Okay. And so what a systolic array does is it doesn't write all the results. Like normally when you do math, you read a couple values, you do some math, and you write it back to the register file.
Okay.
A systolic array allows you to keep intermediate results inside the mathematics itself. So it takes a lot of the pressure off the register file, and you can get a lot faster throughput. It's meant to be sort of a throughput mathematic multiply accumulate.
Cool. Okay. This you called micro benchmarks.
Micro benchmarks, yes. So the problem is, we're trying to improve performance, and if you just look at games, they're super complicated. So if you can't, let's say you're a trainer and you just watch a guy run a marathon, you're like, what do I improve? It's hard. So instead, put him on a treadmill and just monitor the heart and get. So this is our version of that, where we're doing specific instructions, specific functions, and we're making sure that we deliver what we expect just doing those simple things. And so this is a collection of benchmarks that we've ran and comparing Xe to Xe2. So you can see we've had huge improvements in our Execute Indirect capability, Mater dispatch, vertex processing, of course, ray tracing. It's a way to illustrate what did we think that we did before we get to complexities like games.
So is this at an architectural level, these improvements, meaning that it is irrespective of the actual configuration of
exactly,
the...
yeah.
Okay.
This is IP to IP, so it's meant to say, hey, let's say we had one Xe core compared to another Xe core. This is the benefit you would see on that one Xe core at the same clock.
Okay. I remember covering either this exact slide or something similar for the Lunar Lake
Yeah,
stuff.
it's very similar.
And it's probably worth going over some of it again because I could use the refresher. So the big gains you're showing are from compute dispatch and draw.
We call this Execute Indirect in general. And what
these two together?
Yeah, these are both similar, right? They're all basically saying there's a special type of instruction where the CPU can tell the GPU, please basically create this work on the GPU, and it's sort of like a multiplier factor. If you know you're going to do a lot of the similar functions, have the GPU create the work for itself rather than lots of small draw calls on the CPU. It really dramatically shifts the balance of work towards the GPU. It's only useful for compute effectively, but it does have a pretty dramatic effect.
How about pixel blend rate if we just walk down all of them?
Oh, well, this is like on the back end. So when we do blending at the back after you've generated pixels, you got to do things like MSAA or some kind of composition. We've obviously improved our blend rate by 2x.
So then tessellation, I know from just, I think most people in the audience are pretty familiar with tessellation.
Tessellation's great. It's like the expansion of geometry, right?
Right. And what about ray triangle and trace rays?
Well, these guys are all about ray tracing, right? So ray triangle intersection is that process of, you're shooting a ray and you're at the leaf and you're trying to find the triangles that you intersect. Improving that by 2.1x on a per Xe core basis is pretty cool.
What's a leaf?
So when you think about ray tracing, the way we've accelerated it is we have these things called BVHs. And it's remember that bunny picture that I showed?
Yeah.
And you draw boxes around portions of the bunny, and the boxes get smaller and smaller. They're kind of like nested dolls.
Yeah.
And at the very bottom, there are triangles inside that tiniest box. So what you do in your ray tracing is you're traversing these hierarchy of boxes until you get down to the last box. And inside that box, you can imagine there's a list of triangles, which we call leaf. When you're doing a ray triangle intersection, now you've got a list of triangles, and you're going to test the ray against that triangle.
So is the list itself the leaf?
Yeah, the leaf is the final box.
Oh, okay.
And the final box includes pointers to the triangles.
I see. Okay, cool.
So, and that's basically that fundamental operation at the leaf. And then trace rays is the whole path. So it's like, we've improved the overall ray tracing performance by 1.6x.
Okay. So I guess you have intersections and you have the, I don't have the vocabulary.
This is like traversal.
Okay,
right?
traversal.
When you're kind of doing the whole interrogation of boxes and get the whole process of that shader that runs and gets down the leaf, and then you do at the end the ray triangle intersection.
Cool.
Now you can use this technology to implement lots of different effects. Things like ambient occlusion, or you can do global illumination, or you can do shadows. So this is like the hammer, and it's up to you to build the house, right?
Okay,
it's like, what do you do with this? It's all over the place.
Right. And then how about sampler feedback?
Sampler feedback is, again, like how do we get information about textures, and like that feeds back into the pipeline to generate better looking images and reads textures quicker effectively.
Okay. Well, you're talking about like these huge gains, like 12.5x for, I guess, a component of Execute Indirect. What, on the GPU or at an architectural level, what's really driving like a 12.5x increase?
Well, obviously, and when I think about it, we emulated this. So we didn't have direct support for this. So effectively, that means that something is going to have to simulate the expansion of these instructions. And that was very slow. It was slow by 12x,
Okay.
So putting that native capability into the hardware just fixed a fairly significant gap in functionality. At the time we did this, we did not really understand that this new instruction at the time was going to be very popular. And it's now used by a lot of major game engines.
So is this, in terms of like a hardware development life cycle, I guess this is something you maybe run into, or if you start the hardware before something changes in Windows or whatever. So what is that? This is more a life cycle question for the components, but what's that overlap look like? I mean, are you a couple of years into architecture before?
Like, if you think about this right now, Xe2 is launching right now. And first launched with Lunar Lake, right? So it's sort of like a now kind of thing. Xe3 is all done, right? It's the hardware's done. They're basically all baked, and they're on to Xe4. So it's almost like a 2-year minimum gap between decisions on the architecture side and the software ecosystem.
Okay.
So you have to guess what's going to become important 2 years in advance on the architecture side. And it's not really guessing. We're working directly with our partners all the time, but there's lots of moving pieces and there's lots of different people, and sometimes things are missed.
An alchemist.
An alchemist, yeah. But now, much better.
So for something.
Are you looking for a fall guy?
No.
No, because
whose fault is it?
It's me.
No, oh, okay.
No, it's not me.
Okay.
It's all of us. It's all of us.
No, the question was.
It's Damian.
Okay.
I blame Damian.
Got it. The guy who made the excellent slides.
That's right.
And who's answering all the questions
Yeah,
you don't know.
that's right.
It's his fault. Got it. So for Execute Indirect, I mean, as someone who actually, I really don't know anything on the software side at all. So is Execute Indirect, is this something that is defined by like Microsoft? Is it a consortium?
Microsoft.
Okay.
Yeah. So DirectX has a set of draw call definitions, and we work with them, and NVIDIA works with them, and AMD works with them on what are we going to do for these next generation things? And we all agree that these are the right things to do, and then they implement it in a version of DirectX. Okay. Now, what's problematic about that is you agree on the instructions, and you don't really know which ones are going to be the most important ones, because there's a third leg of this triangle, and they're part of this discussion as well. But the game engine developers and game developers are like, how am I going to use this instruction? But they don't have it. They don't have any hardware. They don't have any. So it's sort of like this.
It's chicken or the egg.
I think it could be good someday, but you didn't realize it was going to be fundamental.
Now, is this then something that, does this also translate to Linux, for example, or is this more isolated to DirectX and to Windows?
I think it's every software hardware system has the same problem.
Okay.
Where hardware has to define new things that it thinks are going to be beneficial to software. Of course, it's a partnership, but that hardware has to get built. And then once it gets built, it sits for a while as people learn how to use it. And then somebody walks up one day and says, holy cow, you guys did this?
Why aren't we doing this?
Yeah, and then boom, all of a sudden, everybody's got to have it, right?
Yeah.
So this is one example.
Well, I'm sure that's your early work on frame times, I'm sure was something like that.
I remember AMD had a particularly bad day.
Yes.
Because they did not have a technology that was required to do frame times. And I'm sorry, guys, it's just true. It's just true.
Yeah. Yeah, go look up the old early frame time discussion.
Crossfire stuff.
Yeah, Crossfire,
terrible.
yeah.
Yeah. But this is one of those kind of like, this is pretty obvious in hindsight.
Yeah.
And you'll see it on the next slide.
Let's go to that one.
Okay. So this is the way I think that chart that we just showed is great to talk about microarchitectural things, but it's a little bit hard to really see how does that map to my game, right?
Yeah. Well, and I guess to build on that too, it's kind of like like in a power supply, if you have a component in a power supply that improves its efficiency by 50%, some generational change, that doesn't mean the power supply is 50% more efficient.
Right.
Right. So you're going to see the same thing here, I guess.
Yeah. So this is an example of running Fortnite 1440p. Now this is one frame. Okay, and frames per second, you're doing 60, 100, whatever it is. In this case, this frame had 6,000 or 7,000 draw calls, and draw calls are not draw calls but API calls. So 7,000 commands that the CPU did to create this frame, and those commands are kind of defined by DirectX. And it's like, hey, some are like draw a triangle, some are maybe read a texture, some are maybe execute a shader. But at the end of the day, there's 6,000 of them to get this frame done, and this is time going up. So as this white line goes on, it's doing work. Some things are really hard to do, so it takes a long time, and eventually the whole thing takes 19.3 milliseconds. This is running on Alchemist. Okay.
Now this is an A750 sort of stock spec.
Yep,
I guess.
It's an Intel Arc A750 stock. I think that is 20 cores. Dami, is that 20? 20 Xe cores? 28 Xe cores, okay. And this is the new Battlemage G21 running at 13.01 with 20 Xe cores. Okay, so 28 and 20. And so you can see blue is lower than white.
Which is what we want here.
Which is what you want, and it means it's faster. It's now 13, it's about 30% faster with fewer cores.
So a couple broad questions, I guess. What stands out to me is just this huge jump at the very end of the frame. And so I guess to set the foundation for anyone who doesn't know, we'll keep this brief, but frame times in general and sort of the concept of rendering a frame. So when we talk about like frame to frame interval, you look at the time it might take from one frame to the next, and when you were talking about the microstutter issues and Crossfire, you're looking at that sort of almost like the excursion or the deviation from the mean, like from
Yeah.
frame n-1.
Absolutely.
How bad is it?
Yeah. It's sort of like the next level up from this. This is looking at just that one frame.
Yeah. So it's kind of like the same idea of a chart for frame times across an entire bench pass. You're just isolating for one.
Right.
So.
And now instead of like, if we did another frame after that, it would be this one, and it would just sort of like be up here, right? It would be like over here and do the same thing.
So is this pretty typical in terms of just sort of the shape of the line where at the end you hit this cliff?
This is very typical of modern games.
Okay.
And this is Fortnite, which is using a modern game engine, because a lot of this is compute-based, which is different from new to old. Old games are much more render-based. New games are much more compute-based.
Okay.
So this is a multi-pass render, and I'm going to go ahead and highlight the whole thing. And what you're seeing here is we're highlighting different regions that are showing big differences. And the question is, what's happening, right?
Yeah.
So in this first one, Alchemist is taking 1.16 milliseconds more than Battlemage because it doesn't have support for native Execute Indirect. So that micro benchmark we were talking about before, Alchemist is getting a whole bunch more work that it has to do because it can't do Execute Indirect.
So Alchemist was emulating this function?
It was emulating that function.
Okay.
Yeah, and so that basically took a lot more work on the GPU, and we can save that on Battlemage.
Okay.
Similarly, here in the middle, you're saving another 1.5 milliseconds because time's going up this way. So this line is shorter than that line, or longer than that line, which is the savings, 1.5 milliseconds. Same thing. This was a pre-render pass. Maybe you're building a texture that you're going to use later. This is the base pass, which you're sort of generating your first pass of color. And then down here, when we get a little further, we have a native SIMD 16, which saves 0.3 milliseconds. That's, again, a feature of Battlemage over Alchemist. And we get out here, UAV caching saves half a millisecond, which is huge, for volumetric fog. So just thinking about a modern game engine, they do multiple passes, they're doing all kinds of complex compute functions. A little bit of render is in here as well, and you end up saving about a third.
I guess there is more than just this going on, right? So
There's a lot more.
Yeah, so are you able to give me any sense of perspective? I don't know, if we're talking about 7,000 calls,
Yeah.
what are some broad categories of what those calls are or what they're doing?
Okay.
Because the only one I really know is draw calls.
Yeah, so let's start from a draw call, right? So draw call, imagine that you set up your context, because that's the way to really think about this. There's a lot of calls are about setting up the context for a draw call. You're saying there's some vertices here, there's a texture there, there's there's a shader here, there's a compute shader there, and then all those are all calls. And then once you get all the calls set up, you say, do something. Draw a triangle. Draw a line. Do other kinds of complex drawing things, and then you might say render that to a texture. You've set up your draw calls, and then you say put it someplace. So all of these are creating little tiny blocks of pixels, and then someplace later you're going to combine them all together with another set of draw calls.
Okay.
So you're creating effectively lots of different pictures. And then you're blending them together using draw calls, and you're basically sort of sculpting your image.
Right. Does every one of these calls come from the CPU effectively to the GPU?
Yeah.
Okay.
Yep. The way to think about it is DirectX defines these draw calls, so they're these calls, and the game engine coupled with the basically game itself are doing these series of API calls using DirectX. The way to think about it is the CPU just literally writes out a buffer of bits, and those bits are sitting in system memory, and then the GPU gets tickled and it goes reads those bits.
Is that the technical
word? Yeah, good.
Yeah, right.
Go get it.
Right.
Yeah, go get it. And then they start and then they read those bits, right? And they kind of start executing. Just like the CPU is executing a series of commands out of system memory, the GPU is executing a series of command buffer, basically. Now the driver's in the middle there doing translations between draw calls and things that the GPU can read directly, but it's very similar.
Cool.
Right? This is, to be fair, this is a simplification.
Yeah,
so it's not exactly fair to say that all of this is attributable to native Execute Indirect, but native Execute Indirect does have a significant impact in this region. Similar to here, this is pretty much directly attributable to UAV write caching.
So walk me through that one for the volumetric fog.
Well, if you don't have write caching, then every time you do a UAV write, it actually slows the system down, right? If you don't have enough cache. So improving the behavior of L1 writes dramatically improves our functions of UAV writes.
Okay.
So it's just like how often do you miss? How often do you hit? Do you have to push back to the L2?
UAV stands for?
Unordered access view. And it's basically a way to get rid of sync. Is that all correct, by the way, Tommy? Don't keep me honest. Yeah.
I only know it from Call of Duty.
Yeah, it's a way to avoid synchronization that's normally required when you're reading and writing textures.
Okay.
This is all a compute thing again, pretty much.
Why might deferred lighting? So does deferred lighting correspond with the gain from SIMD 16 here, or I mean, what's the relationship?
So SIMD 16 is the way we're doing our mathematics in the vector unit. And deferred lighting actually takes a lot of parallel computation.
Okay.
And so being native SIMD 16 instead of SIMD 8 speeds up that operation. You don't have quite as much register pressure, and you can actually execute more smoothly. So,
okay. Top level one for you, but to try and answer the comment I saw again.
What was the comment?
So the comment that was the why SIMD and not SIMT?
SIMD stands for single instruction, multiple data. And it's the way, think of it, it's the way math works in our vector unit. You have one instruction and it says do a multiply, and then you have 8 lanes that are going to do that all parallel. That structure is similar between SIMT and SIMD. So think about the math is mostly still SIMD. What SIMT does, though, is it changes the way you do scheduling and you do dispatch. So it's more of a...
The T is thread?
The T is thread,
okay.
yeah. And it's more about like how are you dispatching work and how are you synchronizing work? How does the register file work, schedule? So SIMT is an evolution, I think, of SIMD, and it's very promising. And our architecture is always moving forward and always changing. And I would say there's always going to be something new.
Right, okay, fair enough. I can read between lines pretty well. Anything else on this slide specifically that you want to?
No, I think that's pretty much it. I just want to show you my fancy arc graphic.
Right.
So
this is the Hypnosis graphic.
Look into the circle.
This is where Tom brainwashes all of us. Yes. Do we just stand here and stare at it now?
Yeah, that's it.
Marvel
that's
at it.
You want to go back here? It's better look at it. Here you go.
Yeah, no, I think this walkthrough is really good. I mean, first of all, we've kind of covered stuff like this where you showed a much more complicated version of this in the past.
I did.
You showed varying levels of complexity where one of them was sort of you had this bar chart you were working on at the time. I think it was for PresentMon. It might have been pre-GPU busy and CPU busy.
I think it was, yeah.
Yeah. And we talked about running traces.
Actually, wouldn't it be great someday if we could show the
Yeah.
CPU, GPU busy? We do that now, right?
Yeah.
And this is like the next level of, this is cool to look at because it helps give insight. And if you're an enthusiast, you like understanding how things work.
Right.
I don't know how to represent this in real time because that would be cool. Like,
yeah.
say,
Well, I mean, is this the type of thing when you're designing something like a GPU, and I mean, when you're designing it, you obviously don't have one yet, so you can't just run tests. Are you able to simulate or model the areas? Okay.
Yeah, we have lots of different ways we do it. There's a gigantic emulation farm. So using FPGAs, you can actually run this stuff for real, using the real driver, boot to Windows, and try things out. So the emulation is a key part of this. Everybody does that. Other techniques are architectural models. So we have very accurate, detailed models that are what-if kind of things. If I did this, but the problem with that is, again, you're running in software a very complex model, and it doesn't run very fast.
Right.
So, architectural modeling, emulation, and then just spreadsheets and smart, and
When you actually get the finished product, I mean, I know the answer to this, but does stuff surprise you?
Yes. Yes. There's, I think that's learning. You'd like to not be surprised.
Well, you might be surprised in a good way too, I guess. Okay, maybe not.
I mean, maybe not. I'm surprised that, this such, how many transistors is this thing? 20 billion transistors, right? And the fact that you can build 20 billion transistors, have it go across the world, come back across the world, plug it in, and it does anything is just kind of shocking to me, right? Every time I'm surprised. So, I don't know how many times I've done it, probably 20 times. And it is amazing. And people are literally jumping up and down in the lab every time it happens.
Yeah.
So I'm always amazed at the engineers getting shit done. But, I'm always surprised at things like Execute Indirect. Like, how can you miss Execute Indirect? It's because there's so many things moving. There's this. If you were only doing Execute Indirect, then you would never miss it.
Right.
But they're doing 30 other things too, right? So I would say it's a constant process of getting more efficient, getting better at it. And I'm proud of the impression of, kind of like the improvements that we've made in one generation. If we continue this rate of improvement, because remember, this is a smaller configuration,
Right.
running much faster at the same clock, I feel like we're there,
Yeah. The difference between the A750 and the B580, just by config size, you think of the A580 and A750 is a pretty large gap.
Yes.
So that's excellent walkthrough of it. I appreciate it.
Thank you.
And we will have at least one more video, hopefully, where I think we're going to talk about, I don't know how much I can say if this goes up first. We're going to talk about some cool testing utilities. Actually, I can say LMT.
Yeah, you can
LMT
say
is
LMT.
no.
Yeah,
We're going to talk about LMT.
Yeah, it's going to be great.
Yeah. Thank you, Tom.
Hey,
Much
great to see you.
appreciated.
Yeah, sorry about that. Ugh.
And now that he has his clicker, which I have loaded with expensive Energizer Max AAA batteries, Intel now owes me.
Yeah, I do. Look, lasers.
We will see you all next time.